Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I would like to talk about the basis for vector space. So imagine we have a vector space that can be represented by this circle. So here is a vector space. In order to be called a vector space, a particular set has to fulfill 10 axioms, and this part here I have already discussed in our face-to-face lecture. So there are basically 10 axioms a set has to fulfill in order to be called a vector space. Now inside this vector space, there is another term which we call a subset of a vector space. So this subset here requires us to show that, so this is a subset, and in order to be a subset, it requires us to be able to demonstrate that it fulfills 10 out of 10 axioms, and this here comes directly from this part above here, okay? Now, so let's name this subset as B. So here is a subset of a vector space, and let's say that in particular this subset have different additional characteristic, where we can say that B spans V. The meaning of it really is we are looking at, is it possible to show that all vectors in B, so here in this subset B here we have all vectors, so we will consider all vectors inside B here. Is it possible to demonstrate the linear combination of all these vectors? So in other words, is it possible to show this? Okay, so is it possible to do this? Okay, so that is the question that we need to answer. Is it possible? So if the answer is yes, then good. Okay, we were going somewhere. Okay, so if the answer is yes, then we're going somewhere. And another possible or additional characteristic that we need to consider is so can we show that B is linearly independent? Is it possible to do this? Or in other words, is it possible that we are able to get this mathematical equation? Is it possible that we can consider this, where all Ci is equal to 0? So that's the definition of linearly independent. And let's say the answer to this question is yes. So the question is yes. Therefore, we have arrived at another possible circumstance where we can say that subset B here is a basis for vector space V. So that's the idea of a basis of a vector space. Quite simple really. We need to show two conditions are possible. So the first condition is B spans V, and the second condition is B is linearly independent. Okay. Now, without further ado, let's look at some practical examples related to this idea. So here are the standard unit vectors. So we have the first vector, second vector, and the third vector. So all these vectors here are linearly independent, and this vector here, the set here, spans a real dimension. This vector space is a real with dimension n. Okay, so with nth dimension, and therefore they form a basis of the vector space here, and it is called the standard basis. Maybe to just illustrate what's going on, let's consider a simple case where you have a vector space of 3, and therefore when you talk about the standard unit vectors, you're talking about having a vector E in terms of 1, 0, 0. The second vector is 0, 1, 0, and the third vector is 0, 0, 1. So we need to be able to first show that all these vectors can be expressed as a linear combination. Again, that is related to showing that the first condition here is fulfilled. Therefore, what we can do next is we need to check, is it possible to write down in this condition, really? Is it possible to do this? Okay. So, well, I'm just going to jump ahead and write down. This is C1, 1, 0, 0, plus C2, 0, 1, 0, plus C3, 0, 0, 1. And this is the linear combination of all the vectors. And we can consider that result as perhaps x, y, and z, because we don't know the specific number. So we can just write it down in terms of, or represent it in terms of x, y, and z. And our objective is to be able to find what are the values of C1, C2, and C3. Are these values, do they exist? Okay, so if they exist, then we can say that all the vectors here can be represented as a linear combination, and therefore we can say that the whole thing here is the set here spans this dimension, the vector space of real numbers with 3 dimension. Okay, so what we need to do is we can transform everything into augmented matrix. So we have 1, 0, 0, 0, 1, 0, 0, 0, 1, and here is x, y, and z. And because of the nature of standard unit vectors, the nature of it, it is already reduced to its simplest form. This is already RREF. This is already in its simplest form. Okay, therefore we can say that, well, okay, so based on this we can say that definitely for this one here we can say that C3 is equal to Z. Based on this one here, C2 is equal to Y, and this one is C1 equals to X. Therefore we are able to get the values of C1, C2, and C3. That means all the vectors here can be expressed as a linear combination. Okay, so therefore here is how the representation looks like. We have x 1, 0, 0 plus y 0, 1, 0 plus z 0, 0, 1 is equal to x, y, z. We are able to express all the vectors here in terms of a linear combination, and because of that we can say our conclusion is, we can conclude that the standard unit vectors here span this vector space of real number with 3 dimension or 3 components. Okay, so that's the first part, the first condition being fulfilled. Next we move on to showing that the standard unit vectors here are linearly independent. Okay, and to do that let me just erase this part. Hang on. So for the second condition here, we need to consider, finding, do we have values of C1, C2, and C3 such that the vectors here are all 0. So we have 0 on this right hand side of the equation, and we're looking to see whether C1, C2, C3 are all zeros as well. So in order to solve for C1, C2, C3, again we are going to consider the augmented matrix. Okay, so this is what is going on here. And you can see clearly that based on this augmented matrix, this is already at its simplest form. We don't need to do anything anymore, and you can clearly see that the value of C3 is 0, C2 is 0, C1 is also 0. So that means the standard unit vectors here, so I'm just going to write down some explanation to it. Standard unit vectors here are linearly independent, and because of that we can conclude that the standard unit vectors here, so standard unit vectors here, because of since we have shown that standard unit vectors span this vector space with dimension 3, and they are also linearly independent. Therefore, the standard unit vectors here, I don't have space. Therefore, the standard unit vectors here are basis of this vector space. Okay. All right. Let's move on to the next example. Here we have the vector space of here is the polynomial of degree 3, and I hope you can see that this is the first vector, second vector separated by a comma, third vector, and the fourth vector. So when you have polynomial of degree 3, the construction is basically, or in general, can be written as a0 plus a1x plus a2x squared plus a3x cubed. Okay, so therefore, based on all these vectors given here, so this is the first vector, this is the second vector, third vector, fourth vector, we can represent this vector as such. So this is for constant, this is for x, this is for x squared and x cubed. So when you have 1, that means you have position at this position here, constant, so 1, and the rest is 0, 0, 0. And for this one, for the second vector, you can see that there's only one x here, so therefore the rest is 0, but the position of x, the value is 1. So that is how you can represent that information in terms of vector. Yeah. And this one, you can see that constant is 0, x is 0, x squared is 1, this is 0. And finally, the last vector, vector 4. So here we have 0, 0, 0, 1. And clearly, these are examples of standard unit vectors. Okay, we have position of 1 at that particular, like for example, this one is at position 1, this is at second position, third position, and fourth position, but the rest of it are all zeros. Okay. And I hope you can see that if you follow the same idea as illustrated in this example, you will be able to show that x here is a basis for polynomial, for vector space where it is defined as polynomial of degree 3. Okay, so you have to show the same idea. So the first one is, I'm just going to illustrate how you can do it, and you can do it on your own. So first of all is you must show that x spans P3. How can you show that? You have to find or you have to be able to write this sort of equation. So combination of this, okay, and this one, this is for the third vector, and this one is for the last vector, And you need to be able to write all of them in terms of a linear combination where the result is going to be something. We don't know what that is. We can just call it XYZ. Hang on, I cannot call it XYZ. We don't have enough alphabets for that. So we can call it WXYZ. And your objective is to be able to find what are the values of C1, C2, C3, and C4. Do they have values? If they do, then we can say that you are able to express all the vectors here in terms of a linear combination, and because of that, X spans the vector space here of polynomial degree 3. So that's the first condition that you have to fulfill. Next, if you have managed to do that, what you need to do next is you need to show that X here is linearly independent. So the set X is linearly independent. And how can we do that? You need to be able to construct, again, a bit of similar idea. Okay, so this one, you need to be able to do this. Okay, and instead of having WXYZ, here is 0, 0, 0, 0. So we have vector 0 on the right hand side of the equation. And your objective is to try and get the values of C1, C2, C3, and C4, and are they equal to 0? Are they equal to 0? If they are, then we can conclude that set X is linearly independent, and if condition 1 and condition 2 are fulfilled, you can then demonstrate clearly that this is a standard basis for vector space of polynomial of degree 3. Okay, now I shall look at this example. This is the last example that I would like to talk about in this video. So here we have set S, and this is the first vector, and this is the second vector, and the aim here is to show that set S here is a basis for a vector space, where here we're dealing with real numbers and the dimension is 2. Okay, so again, the starting point is to show that S spans this vector space. So that is what we're looking for. What we have to do, well, and our starting point here is going to be C1 1 1 plus C2 1 negative 1, and this is equal to something. We don't know what it is, so I'm just going to call it X and Y. Okay, so that is our starting point. Next, we're going to consider the augmented matrix. So here we have 1 1 1 negative 1 X and Y, and what I'm going to do is well, this part here can be turned into 0, so we have R2 plus negative 2 R1, and here we have 1 1 X, and here we have 1, sorry, not 2, 1. So here we have 1 minus 1, 0, negative 1, negative 1, negative 2, Y minus X. Okay, next what I can do is I would like to focus on this part, turning it into positive 1. So therefore, here it will be multiplying the second row with negative 1 over 2. So we will have 1 1x 0 1 y minus x over negative 2. Okay, right, and therefore, based on this, we have obtained a solution. So the solution is for C2. C2 is equal to y minus x over negative 2, which can be written as x minus y over 2. Okay, so this is the same thing. We have x minus y over 2. Next, if you consider this part, this is having C1 plus C2 is equal to x, Therefore, C1 must be equal to x minus C2, which is x minus y over 2. And this is equal to, if you simplify that, so 2x minus x, you will get x plus y over 2. So that is the solution for C1. Okay, and since we have the solution for C1 and C2, well, you can actually express these two vectors here in a linear combination. So how does it look like? So it looks like this. We have, therefore, we have x plus y, over 2 times with vector 1, 1, and then plus x minus y over 2. So here is x minus y over 2, and here is the second vector. This is equal to x and y. So since we have managed to show that, we can clearly see that the two vectors here can be expressed as a linear combination. Therefore, as a conclusion, S spans this vector space. Okay, so S spans R2. Okay, so that's the first condition. Next, we are going to demonstrate that S is linearly independent. Okay, so to do that, we need to consider the starting point here, where you have the first vector multiplied with C1 plus C2, 1, negative 1, and the result here must be 0 vector. So we need to solve for C1 and C2. What are the values? And you can consider the augmented matrix, except that at this position, this is 0 and 0. So basically, we have the same starting point for this part here, except the difference is that for this one here, we have already done the one on the right hand side here is x and y, but this one is 0 and 0. So if we let x equals to 0 and y equals to 0, then we can use the solution that we have obtained in the previous condition, in the previous part, part of showing that S spans the vector space here. So I'm just going to let x equals 0 and y equals 0. Therefore, C1 that we have obtained just now, this is C1, x plus y over 2 is equal to 0 plus 0 over 2, which is equal to 0. Okay, so I'm just going to write down a bit, consider the augmented matrix given as such. And then you can recognize that we have the same starting point as what we did here just now. So therefore, the difference is that the values here are 0. So if I let x equals to 0 and y equals to 0, I should be able to use the solution which I have already obtained in the previous part. So therefore, I'm able to show that C1 is equal to 0, C2, which is x minus y over 2, is equal to 0 minus 0 over 2, which is 0. Since what we have is trivial solution, we can say that S is linearly independent. So we can conclude as a conclusion, S is shown to be linearly independent, since condition 1 and 2 are fulfilled. Therefore, we can say that S spans this vector space of real numbers with two dimension. Okay, I think that's all for now, and I will go on with more examples related to this idea, basis of a vector space, in the next video. So I'll see you then.